Hello and welcome to today's lecture. So we're going to start by a quick review of what we were talking about last time. And so we'd moved on from talking about heat engines, where we want to take heat and partially convert it into work, to talking about refrigerators, which in some sense you can think of as the same kinds of thermodynamic cycles that are responsible for heat engines, but run in reverse, so that in this case, we're actually having the gas perform negative work. So we're performing work on the system, and the net result is we're actually able to extract heat from a colder part of the system, a cold reservoir, and put it into a warmer part of the system, which we think of as the hot reservoir. And so in applications, the cold reservoir could be the inside of a refrigerator, and the warm reservoir could be the air in our room. Or in an air conditioner, the cold reservoir could be the inside of a home, and the warm reservoir could be the exterior. And so I want to start by reviewing just the very most important step in this cooling process, just so we can understand the physical reason why we're able to use one of these gas processes to actually keep something cool. And so in our example of the Stirling cycle run in reverse, the crucial step was a constant temperature expansion of gas. So we had gas in a cylinder in contact with our cold reservoir. And now we pull up on the piston slowly. And what happens is that heat from the colder reservoir flows into the gas in our cylinder as we do that. Okay. So how can we understand this? Well, there's a couple of ways to understand it. And first, let's talk about a different kind of a process where instead of pulling up slowly on the piston, we pull up quickly on the piston. Okay. And so this would be an adiabatic expansion. And what will happen in that case is that during the adiabatic expansion, the gas in the cylinder will actually cool down a lot. And the reason is that for an adiabatic expansion, Q equals 0, and the change in internal energy then is equal to negative W, which is positive because we have an expanding gas. So the gas is doing work on the piston during this adiabatic expansion. And so it's giving up some of its energy because there's no heat transfer in the process. That decrease in energy is going to be a decrease in internal energy of the gas, and so the temperature will decrease. Okay. So if we pull up on the piston quickly, then we expect that the gas in the cylinder will get a lot colder. This is like the opposite of the adiabatic compression demo that I did, where I was able to heat up air a great amount simply by doing work on it. So here the gas is doing work, it cools down, and then afterwards, because it's in contact with the 0-degree reservoir, there'll be heat that flows in from the cold reservoir into the gas, which is even colder, to bring it back up to 0 degrees. The constant temperature expansion, you could think of that same kind of process, but slower, where the cooling due to expansion and the transfer of heat are happening kind of at the same time. So if we think about this slow process as a very small adiabatic expansion followed by heat going in to bring it back up to 0, then we can understand that the temperature of the gas in the cylinder is going to remain at 0, but we're going to continuously be taking in heat from the cold reservoir. Okay, so those are two different ways that we can achieve this cooling of the cold reservoir, and it basically comes from the fact that our gas in the cylinder is doing work on the piston as it's made to expand. So there's actually an interesting demo that allows us to understand this phenomenon. So the thing we can do here is first put your hand close to your mouth and then breathe out slowly. And so you can feel the temperature of the air coming from your lungs. It's quite warm. It's likely to be quite a bit warmer than the room that you're in because our body temperature is around 37 degrees Celsius. Next, what I want to do is have you put your hand a little bit further away, and now purse your lips and blow as hard as you can and feel the temperature of the air that hits your hand. And so you could hopefully feel that that air is quite a bit colder than the air that was coming out when you breathed slowly. So what's going on here? Well, this is an example of adiabatic expansion of air coming out of your lungs. And so by blowing hard, you're forcing the air to move quickly out of your mouth. And now it's exerting forces on the surrounding air. And so it's doing work on the surrounding air. When it does work on the surrounding air, that energy comes from the internal energy of the gas. And so the gas temperature decreases. So it's very easy to demonstrate this cooling of gas that happens when you have adiabatic expansion. If you've watched any of the old Superman movies that were on when I was a child, then one of Superman's superpowers is this super freezing breath. Excuse me. And so Superman was actually able to blow air so hard that he could then freeze objects. And well, this is actually a real phenomenon. So if you were able to blow with enough force, then the air would in fact cool down enough to freeze things. Okay, and that's really what's happening in an actual refrigerator, as I'll mention in a couple of slides from now. Okay, so what I want you to understand here is just this basis of cooling that appears in any kind of refrigerator or air conditioner. And the essential part is an expanding gas doing work on its environment and therefore cooling down. And after that, it takes heat in from the reservoir that you're trying to keep cold. Now, in an actual refrigerator, that's part of a cyclic process. So we want to take in this heat from the cold reservoir, but then we have to get rid of heat somehow. And we do that by next placing the gas in contact with the warm reservoir. And so you see in this step, we have thermal contact between the gas and the cold reservoir. In the next step, we're going to put the gas in contact with a warmer reservoir, and then we compress it either adiabatically or isothermally. And during this compression, what happens is that now we do work on the gas, we add energy to it, and this energy is now transferred into the warm reservoir. And so we just keep repeating that. We expand the gas, it takes in energy from the cold reservoir, and then in contact with the warm reservoir, we compress the energy, sending energy out. And so overall, we have this kind of a diagram where in each cycle, a certain amount of energy is taken from the cold reservoir and placed into the warm reservoir. And so it almost seems like we've managed to get heat to flow from a cold object to a warm object, which we said never happens. But the trick here is that we've had to do some work on this system in order to achieve that. Okay, and so the net work, the net W for the cycle is negative, meaning the gas is actually taking in work from the environment. And that work is work that we have to do. We have to provide the energy in order to do that, in order to, say, compress the gas and pull and expand the gas. Okay. So that's the basic energy diagram for a refrigerator. And we see in the end, the net result is that we do some work. And then by doing that, we're able to transfer heat from the cold side to the hot side. Okay, so in an actual refrigerator, what we have is that instead of having the gas in some fixed compartment and then placing it in contact with the cold and then in contact with the hot side, instead what we do is we have the refrigerant move around through some tubes, and the expansion and the compression take place in different locations. And so here, instead of just air, we usually have some particular refrigerant chemicals. And so they move through these tubes. Sometimes they're in gas form, sometimes they're in liquid form, but the essential steps are still the same. So what happens is that there's a high pressure side and a lower pressure side. And this expansion valve here is a place where the high pressure fluid is allowed to adiabatically expand into a lower pressure side. And that's the place then where your refrigerant cools down dramatically. Then it's sent through tubes connected to the inside of your refrigerator. Okay, so here it takes heat in from the inside of the refrigerator, and so the refrigerant then warms up from a temperature which is colder than the fridge back up to the temperature of the inside of the refrigerator. Then it comes to the compressor, and so this is the place where you are adding energy. So you have a motor that runs the compressor. That's a piston in a cylinder, for example. And this thing now compresses the gas and therefore increases its pressure, increases its temperature. And now it's sent through tubes which are thermally in contact with the outside of the refrigerator, with the air in your room. And so the heat that you add, the energy that you add here is then distributed outside of the fridge into the surrounding air. And so it just keeps going around. And so you have adiabatic expansion. That very cold fluid cools the cold reservoir, the inside of your fridge. Then you have adiabatic compression, and then you give up that heat to the air in the room. Okay, so that's basically how a fridge works. An air conditioner is just the same thing, except it's like a refrigerator on the wall of your house, where the inside of the fridge is your house and the outside of the fridge is the outside air. And generally speaking, you also have a fan that then distributes the air that you're cooling throughout your house. Okay, well, here's a quick question about refrigeration. A real world scenario. The question is, can you take a refrigerator and have that in your house and just open the door of the refrigerator in order to cool down your house? And so, take a minute to read through these options, and then we'll talk about what happens. Okay, so you might think that this is a good idea, because if you do open the fridge, then you get this cold air, and it temporarily at least feels colder, and it seems like maybe that would be a good way to cool your room. But if you think about it more, you realize that overall, in terms of energy, what the fridge is doing is it's taking energy from inside the refrigerator and just sending it out the back of the refrigerator. So it's transferring heat from the inside to the outside. But then there's also this extra energy that you're producing by operating the motor, by operating the compressor in the refrigerator. And so you're adding extra energy through electrical power. And so the actual amount of energy that's coming out of the refrigerator is more than the amount of energy that you're removing from the air. And so basically, if you just had the fridge in your room with the door open, there would be energy taken from the inside and then heat would flow and be transferred to the back of the refrigerator. Okay, so it's just coming from your air on one side into the air on the other side, but then you're actually transferring even more heat than that, because you're also doing work inside the refrigerator and you're adding energy through this electrical energy running the motor. And so generally speaking, what you'd expect is that you're going to actually heat up your room if you open the fridge door and just leave it running. And you might ask, well, okay, that's not good, but is it any worse than if the fridge door is closed? So even then, with the fridge door closed, you're going to be heating up your room. But it's worse to have the door open, because the way that the refrigerators work is that the motor only runs when the temperature inside the refrigerator gets above a certain point. So with the door closed, the motor doesn't run as often, and so the temperature so the temperature stays cool with less work being provided. But with the door open, then the temperature inside the door, it's probably always going to be above the temperature at which the motor runs. And so the compressor in the fridge is going to run continuously, and you'll just be adding more energy than you would have been adding even if you had the fridge with the door closed. Okay, so the answer is D here. that really that's the worst thing you could do, except for that initial blast of cold air that you get. Overall, then having the fridge with the door open is going to be a really bad idea for trying to keep your house cool. Okay. But as I mentioned, an air conditioner is basically just that same thing, but you make sure the back of the fridge where the heat is being expelled is the outside of your house. Okay, so that's not such a bad idea if you do it in the right way. All right, so we're going to now move on to our final topic in thermodynamics. And this is going to help us understand the question of why, from the refrigeration point of view, why you always need to do work in order to transfer heat from a cold object to a hot object. And it goes back all the way to our first week when we said that heat always flows from hot to cold. And so we're going to try to understand why it is now. Why can't we ever observe heat simply flowing from a colder object to a hotter object? So I want you to think first in terms of conservation of energy and whether that kind of a process would violate it. Is this consistent with, say, the first law of thermodynamics? So take a moment to think about that, and then we'll discuss the answer. Okay, so the answer is that it wouldn't violate the first law of thermodynamics. In principle, I could imagine taking some energy here from the colder object and transferring it to the warmer object. And as long as that amount of energy is that I take out of the cold object is the same as the amount of energy that goes into the warm object, then energy is going to be conserved. So I could imagine a process where I take 100 joules of energy from the cold object. Maybe then the temperature of the cold object must decrease because I'm removing energy. I could calculate the decrease in temperature by saying that Q equals mc delta T. And then I'd be adding that Q to the warmer object, and its temperature would increase, and everything would make sense with the first law of thermodynamics. So the reason why heat never flows from cold to hot, it's not because it would violate energy conservation. It's not because of the first law of thermodynamics. There's actually a completely separate reason why we never observe this. Okay, and this is related to what's called the second law of thermodynamics and to the concept of entropy. So this is our question. If we want to understand it, if we want to understand why heat always flows from the hotter object to the colder object, we need to understand something a little bit different than just energy conservation. Okay, so maybe think about this a little bit on your own. Why does heat always flow from hot objects to colder objects? And we'll be talking about this then for the rest of the lecture. Okay, so I won't reveal yet the answer, because I want first for us to understand an analogous situation. And so in physics, it's often true that in order to understand some observed phenomenon, we can actually understand that by thinking of a simpler situation where the same phenomenon occurs. And that's sort of the purpose of this demonstration that I'm about to show you in the form of a video. Okay, so let's watch this, and then we'll understand how this video relates to our question. So in order to understand why heat always flows from hotter objects to colder objects, it's going to help if we first understand frogs. So here's a simulation of a frog. And the main thing to understand about this frog is that it's hopping around randomly. I don't know about real frogs, but this frog is definitely hopping around randomly because I programmed him to do so. Points in a random direction and then hops. And if we watch the frog, sometimes he goes to the left and sometimes he goes to the right. The right-hand side happens to be orange and the left-hand side happens to be blue. It's not actually any hotter on the right or cooler on the left. We can see that the frog doesn't seem to prefer one side or the other. As I said, he's simply hopping around randomly. But now let's see what happens if there are many frogs. And so in this simulation, we start with 150 frogs on the right and 10 frogs on the left. And we could just watch what happens. It's going to take a while, so it'll be helpful if we make the frogs speed up a little bit. And so what you notice is that overall, there seems to be a flow of frogs from the side with more frogs to the side with less frogs. And after a while, even though there were many more frogs on the right-hand side initially, there are going to be roughly the same number of frogs on the right-hand side and the left-hand side. And it's not just a fluke. We could repeat the experiment as many times as we like, again, starting with 10 frogs on the left and 150 frogs on the right, and we can speed up the frogs, see what happens. And so, again, we see that as time passes, we seem to get more and more frogs on the left-hand side. And if we wait long enough, then the number of frogs on the left is approximately equal to the number of frogs on the right. So if we can understand why the frogs in the simulation always seem to flow from the side with more frogs to the side with less frogs, that's actually going to give us the understanding of why heat always flows from the hotter side to the colder side if you have an object, or from the hotter object to the colder object if you have two objects together. Okay, so let's get back to our slides here. Now we're going to understand the question about frogs, and we'll understand the analogy between the frogs and our heat flow situation. And so eventually we'll understand exactly why the heat flows from the hot side to the cold side. So thinking about this frog simulation, what we started with was a situation where there were many frogs on the right-hand side and just a few frogs on the left, say 10 frogs on the left. And we observed that we always went to the situation where there are more frogs than there used to be on the left and less frogs than there used to be on the right. So to understand why, we can go back and think about the individual frogs. So the individual frogs were really just hopping around randomly. Those frogs didn't prefer in any way to be around fewer frogs. It wasn't even programmed in that the individual frogs would be able to tell if there were frogs around them or not. So all of these frogs were basically just behaving independently. And yet, when we observed the final results, then we seem to have this net flow of frogs. So because the individual frogs are moving around randomly, if we think about letting this simulation run forever and ever, just a long, long time, eventually we would explore all of the possible configurations of frogs. So we can imagine like all of the possible places where you could put 160 frogs. And then we could start to ask, well, how likely are the different possible configurations? And so basically, any specific configuration, like this one where all the frogs happen to be on the right, and this one where they're distributed in a different way, I'm just as likely after 1,000,000 years to end up on this configuration as I am to end up on this configuration. If I look at any specific configuration, they are all equally likely. However, if I ask how many configurations are there that look like this one versus how many configurations there are that look like this one, then it turns out there are way more configurations that look like this one with an equal number of frogs on the left and right, compared with configurations like this one, where I have many more frogs on the right. Okay. So mathematically, just as an aside, if you're familiar with combinatorics, then if I have, let's say, 10 to the 5 possible pixel locations for each frog on each side, then on the right-hand side, the number of configurations is just the number of ways to choose 100 things out of 10 to the 5 things. Okay, that's 100 choose 10 to the 5, or 10 to the 5 choose 100. And on the bottom, I just have to mathematically count the number of ways of choosing 50 things out of 10 to the 5, and then another 50 out of a different 10 to the 5. So those are fairly standard combinatorical calculations. And what you find is that the number of ways that it's possible to choose the frogs to be all on the right is something like 10 to the 500, whereas the number of ways to distribute the frogs with 50 on the left and 50 on the right, considering the different possible locations, is something like 10 to the 530. So these are both enormous, enormous numbers that are hard to imagine, but you see that this one is way bigger still than this one. Okay, so there are 10 to the 30 more configurations with an equally distributed number of frogs than configurations where they're all on one side. So I've tried to indicate this in a diagram, which is actually woefully insufficient to indicate this, but this is supposed to represent all of the possible configurations of the frogs, and then this red dot, which should be much, much, much smaller, that would indicate the configurations where you have all of the frogs on the right-hand side. Okay, and so now you could think, well, we're going to start with 10 frogs on one side and 150 on the other, or 90 on the other. So, and then just let it go, let all the frogs hop around, and then just see what happens in the end after a long amount of time. Okay. And so as we let the frogs hop around, we just move between possible configurations. And you can ask, well, what are the chances that you're going to end up on one of the ones with all the frogs on one side? So the chances are very, very small. The chances are like 1 in 10 to the power 30, because it was only that fraction of the possible configurations where all the frogs were on one side. So essentially, there's basically no chance. You know, it's like winning the lottery 3 times in a row. There's basically no chance it will happen that you find all of the frogs on the right-hand side, even though it's mathematically possible for it to occur. Okay. So this is our understanding of why it's observed that frogs seem to flow from the region of more frogs to the region of fewer frogs. What we can say is that all configurations of frogs are possible, but it's just that there are vastly more configurations with a more balanced number of frogs. And so if we start with an imbalanced number, we're almost certain after a long period of time to end up in a configuration with a more balanced number of frogs compared to the situation of ending up with a less balanced number of frogs. There are simply way more such configurations. So now we want to apply our understanding of the frog situation to the actual problem, the physical problem of why heat flows from higher temperature objects to lower temperature objects. So take a moment to think about what these frogs might represent in terms of that thermodynamic situation. So the answer is that the frogs represent energy. So when heat flows from one side to the other, it's really energy being transferred from one side to the other. And we can think of it being the transfer as happening because of the interactions between the molecules. So when we have collisions between nearby molecules, we can transfer from some energy from one to the other. And so in a thermodynamic system, the energy is randomly moving around due to these interactions between molecules. The units of energy are just like the frogs in that they can move anywhere in the material, and their motion of the individual units of energy is basically random. Okay, so both the frogs and the energy, while they're conserved and they move around randomly. The analogy with the number of frogs or the density of frogs is that that would correspond to the temperature. Because remember, temperature is a measure of the amount of energy per molecule. And so in that case, it's like the density of these little e's. Those are say units of some unit of energy. And so the number of units of energy per molecule would, in the frog analogy, correspond to like the density of frogs. Okay, and so so basically, the same explanation then applies to say that if we start out with a higher density of energy on this side, which means a higher temperature, then we're going to have heat that flows from the higher temperature side to the lower temperature side. Okay. So let me just summarize the argument then. We can say that in a thermodynamic system, energy is exchanged between nearby molecules by some random process. This is like a hopping frog. And then the reason why we see that energy always flows from hot to cold is just that there are vastly more configurations where the energy is distributed more evenly between the two sides. And so if we start in this situation with 20 degrees and 80 degrees, then mathematically it's possible, it doesn't violate energy conservation to go to 10 degree, 90 degree, but it'll never happen because the number of microscopic configurations corresponding to that 10 degree, 90 degree case is far, far less than the number of microscopic configurations where the energy is more balanced. Okay. And so you're always, in practice, going to observe a flow to a situation where the energy is more balanced between the two sides. We can actually be a little bit more quantitative about this using the concept of entropy. And so I mentioned earlier that in the frog case, if we have, say, 100 frogs, then there are 10 to the 500 configurations where all the frogs are on one side, and about 10 to the 530 configurations where the frogs are equally distributed between the two sides. So entropy is simply a measure of that number of configurations. More specifically, you just take the number of configurations, you take the logarithm of that number, and that is a microscopic definition of what it means to say, to talk about the entropy of a configuration. Okay, so it's a measure of how many possible microscopic configurations there are for a specific set of macroscopic variables. You know, in this case, it's like the number of frogs being 100 on the right-hand side. We can associate an entropy to that by counting the number of such configurations. And the entropy is just the logarithm of this number of configurations. Okay, so the entropy would be about 500 in this case here. And in the other case where the number of configurations is 10 to the 530, we would say that the entropy is 530. So it's kind of like the exponent it's the power of 10 in our number of configurations. Now, in the actual thermodynamic situation, you might imagine that there are far, far more configurations when we start talking about how many actual configurations there are of molecules, or how many ways are there to distribute a certain amount of energy among the molecules in a solid. Okay, in that case, there's like enormously more than this 10 to the 500 number is tiny compared to the number of configurations that we're talking about. And so in this case, say, the number of configurations that have 30 degrees on one side and 70 degrees on the other side, number of ways to distribute that amount of energy such the average energies are in this sort of 3 to 7 ratio, it turns out this number, I don't even know what that number is, 10 to the like quadrillion, quintillion, septillion or something, 10 to the septillion times more likely. So there's 10 to the septillion times more configurations of energy in a pair of bricks here with these temperatures than there are configurations of energy in a pair of bricks with these temperatures. And so if you start in this situation and you let the energy move around randomly, of course, you're never going to end up here. You will be this many times more likely to end up in a configuration like this. Okay. And so this is the nature of the second law of thermodynamics, which basically says that you're just always going to, the thing that will happen is the one that's going to have almost infinitely more probability. The statement is that total entropy never decreases. And that's just a statement about probability, that you never end up seeing these things where the probability is 1 over 10 to the billion or trillion or quadrillion. Okay, so total entropy decreases just means that you're always going to go to these almost infinitely more likely situations. Okay. So next time we're going to get into some more quantitative discussion of entropy and how it can be useful for us in analyzing thermodynamic processes. And we'll later relate that to questions like, why can't you have a perfectly efficient heat engine, or why is it always necessary to supply work in order to have a refrigerator? So that's all for today, and we'll see you next class.